This lesson is about plane electromagnetic waves. So we want to study the simplest solution to Maxwell's equations, and we find that the simplest solution takes the form of plane waves. Waves are actually a consequence of Maxwell's equations, and the general equation for the waves is a little more complex than what we see here. So that we see a simplified version with a specific dependency on space of the fields, but the general properties of the solutions, the term of plane waves, are shared also by the most general wave function that we could find as a result of Maxwell's equations. So we start with Maxwell's equation in the absence of sources, so that, as you see, we have electric sources here. We can get rid of this term and obtain an equation, a couple of equations that link the two fields E and H. One is Faraday's law, that is here, and the other is Ampere-Maxwell law, that is here. Now let's assume that the electric field, for instance, which is a function of position, has a single direction in space, for instance, the x direction, so a single component, and is a function of position of a unique variable of space, for instance, z. Of course, it's a very simple form, but it allows us to write down a set of equations that are easily solvable and that tells us a lot about the solution in terms of waves of Maxwell's equations. Once we establish that the electric field has this shape, we can easily find that the curl of E is a y-directed vector whose component is the z derivative of the x component of the E field. And since the curl of E equals minus j omega mu h, this means that the magnetic field is y-directed and is only a function of z. So that once we substitute this into this equation, we obtain a very simplified expression for Faraday's law, which is simply the z derivative of Ex, and it must equal minus j omega mu hy. Similarly, for this shape of the magnetic field, we can apply the curl and find a very similar expression for the equation corresponding to Ampere-Maxwell law. In particular, the z derivative of hy must equal minus j omega epsilon Ex. These two equations can give rise to waves. Let's suppose that epsilon and mu are real, so that we are not in the presence of losses. In the presence of, therefore, ideal materials, we can write down these and observe that this coefficient that multiplies hy is purely imaginary, and so is this coefficient that multiplies Ex. So if we take a second derivative with respect to x, and we see it here, this must equal minus j omega mu, a purely imaginary term, that multiplies the z derivative of hy. But the z derivative of hy is a function of Ex, so that we can substitute here and obtain that the second derivative of Ex with respect to z twice equals a term, which can be written a real coefficient minus k squared, can be written as minus k squared, whose value is omega squared times mu times epsilon, that multiplies the same function Ex. What is the general solution to this equation? It can be written in the form of two exponential functions. And we give a name to these two functions as progressive wave and regressive wave, because this represents something that moves in the positive direction of the z-axis. And this represents something that moves in the negative direction. These two coefficients are unknown coefficient, complex coefficient, that represents the value at z equals 0. So let's focus on the progressive wave, and in particular we write again this wave here, in which k is omega, the square root of mu epsilon. So what is the time domain function that represents, in the time domain, this phasor? We have to take the phasor, multiply times exponential j omega t, and take the real part. This is the real part of A plus. A plus can be complex, so it has a magnitude and also a phase, and then we have this exponential function. Of course, the real part is the cosine function, so that we have that the time domain, but also function of z, Ex, x component of the electric field, has a magnitude, an amplitude, that is the magnitude of A plus, times the cosine of omega t minus kz plus a constant phase phi. This can be seen as a sinusoidal function of time and space, because let's fix ourselves at some point in space, z, fixed, doesn't change, let's let time goes by. If time varies, we observe a sinusoidal variation with time. So if we plot on the horizontal axis time and we plot the cosine of omega t, we observe a sinusoidal function, which is the green function that we see here. The period of this sinusoidal function is capital T, 2 pi over omega. Similarly, if we fix time to a specific instant, and we move along the z-axis, we similarly see a sinusoidal function of z. That is this orange function that we see here, in which k, in the space domain, plays the role of omega in the time domain, so that we have a space period, which is called lambda, which is exactly 2 pi over k, similarly to what we did before, in which capital T was 2 pi over omega. This space period is so-called wavelength. And k, which takes the role of omega in time, so it can be seen as a space angular frequency, is also called a wave number. So why this function moves along the positive direction of the z-axis? Because if we manage to move on the z-axis, we let time go by, and we move along the z-axis so that the argument of this function is kept constant, also the value of the function itself is kept constant. So if we manage to move along the z-axis at the same speed of this function, we must see a constant value for the function itself. Which means that we must find, for this to happen, we must move at specific speed that is found by imposing omega t minus kz equal to a constant. By differentiating this expression, we obtain omega dt minus k dz equals 0, which means that dz over dt, which is the speed at which we move along the z-axis, must be equal to omega over k. We call this speed v, and by substituting the expression for k, which is seen here, we obtain as v 1 over the square root of mu epsilon, which is the speed of electromagnetic waves in the material, also called speed of light in the material. This speed takes the well-known value 3 times 10 to the power 8 meters per second when we are in vacuum, which is speed of light in vacuum. The other function, the function that has a plus sign in the exponential, is a wave that propagates along the negative direction, because as you see here, by applying the same procedure that we saw before, in order for us to see the constant value for the argument of the function, when t increases, we will move towards a negative value of z. We must decrease z so that this is kept constant, so that this propagates in the negative direction of the z-axis. So now that we have an explicit value for the dependency of Ex, we can substitute back into Maxwell's equations the z derivative, because as you see, the z derivative of Ex is now, in this case, jk, for the case of the progressive wave, minus jk. So we can substitute its value and obtain a relationship between Ex and Hy for the positive wave and for the negative wave. This relationship takes the form of omega mu over k, so Ex for the positive wave is omega mu over k times Hy for the positive wave, and this term, omega mu over k, is called eta, whose value is the square root of mu over epsilon once we apply the expression of k that we found previously, and is called wave impedance. Sometimes it's also called impedance of the material, because as you see, this parameter is only dependent on the property of the material. Of course, the largest possible value for the speed of our electromagnetic waves that we find from Maxwell's equation is the speed of light in vacuum. But for the vacuum, this corresponds to mu naught over epsilon naught, which is a number that is well known as 377 ohms in free space. So that we have our wave that can be plotted like this, something that propagates along the positive direction on the z-axis. We have a direction for the electric field, and the direction for magnetic field, these two are orthogonal, and they are orthogonal to the propagation direction. This is called a uniform wave. There are some other waves that do not share the same properties, but this is the most important wave that originates from Maxwell's equations. This is the wavelength, as you see, and this is, we summarize the expression for E and for H, functions of unique parameter A+. Let's not forget that the electromagnetic waves is not made separately of an electric and magnetic field. They travel together because they are mutually induced, electric and magnetic field, so we should speak of electromagnetic waves and not electric wave or magnetic wave, in which there is a unique parameter that governs the wave. In our case, it's A+. Associated to this wave, there is also a power density that you can obtain as the real part of the projection of the Poynting vector on the direction of propagation. It takes this form, and if we substitute the expression for H as a function of E, it takes also this form. Similarly, if you observe what happens in the field, in the transverse plane, transverse to propagation, for the direction of the electric field, we can have several cases. So we speak of polarization of the wave when you look at the direction of the electric field for a fixed value of the coordinate z as a function of time. If this direction of the electric field as a function of time doesn't change with time, we speak of linear polarization. Now, if it changes with time, you can have circular polarization or elliptical polarization and no other cases. So in the field, in the plane transverse to propagation, there can be two components of the electric field, x and y component. If their magnitude is the same, and if the phase shift is plus or minus pi over 2, we have circular polarization. Otherwise, so for instance, different magnitude of different phase difference between the two direction of the electric field, we have elliptical polarization. What are we meaning with this? For instance, if you have a pi over 2 difference in the phase of the electric x component and y component, it means that when x component is maximum, y component is 0, and vice versa. So this means that the electric field at a fixed position of space will change over time. And in its changes, since the two amplitudes are the same, it describes a circle. This is the meaning of circular polarization. And similarly, we can define elliptical polarization.